Well friends, I am sure you are enjoying this course. While going through the lectures, I have also given some examples. Dr. Amandeep Singh is also dealing with some of the problems which is related to the lecture what we have covered. In the examination, we will try to have maximum 2-mark problems. So, if it is a 2-mark problem, there will be 1 step or 2 step. The magnitude for every term will be given in the examination. The units are something which you should try to have it in your mind. So, when we give the problem, there can be a mismatch in the units. So, you have to normalize and then try to solve. Okay. So, now getting into the new lecture, it is going to be on vapor power cycle. When we talk about vapor, we always try to talk about steam. Why so? Because friends, you saw in the previous lectures, we have dealt with thermodynamic property table. So, it is a huge table. Generation of so much of data is going to be very difficult for all fluids. So, people have picked up few of the working fluids and then they have given the table. In our case, since it is a basic fundamental course, we will keep always with respect to water. So, now we will try to see steam based vapor power cycle. So, cycle means there are processes like pumping, expansion and compression, all those things will come. Power is what is it generated out of the cycle will be power. The content of this lecture is going to be vapor power cycle. Then we are going to go through Carnot vapor power cycle. Then we will try to see Rankine cycle, then modified Rankine cycle, then binary vapor power cycle, binary means 2, binary vapor power cycle, then ideal jet propulsion cycle which is used in planes. Vapor power cycle forms the fundamental basis of thermodynamic analysis of steam power plant, widely used to generate electrical energy and industrial processes. So, what happens exactly here is people start with coal, they burn coal. When you burn coal, they will try to heat water. From the water generates steam. From the steam, it is tried to hit against a turbine blade or a turbine. From the turbine blade, we try to connect it with a generator, and from the generator we try to generate electricity. So, this is how it goes. So, we always call it as a thermal power plant. Thermal power plant, we try to use either directly gas and other things or boil water, convert into steam and then try to use it. This cycle operates on the principle of phase change. So, water converted into steam. So, typically involving vaporization as a process. When you convert a liquid to a gas, so it is called as vaporization. When you do it reverse, it is condensation. Vaporization and condensation of a working fluid, of any fluid, that is what I discussed in the beginning, but we are comfortable with water. So, we take water, which allows the efficient energy transfer and high thermal efficiency is nothing but vapor power cycle. As I told you, there will be a pump where water is pumped into the system, then the water is taken to the boiler where there is a phase change. You can have single phase, 2 phase, generally we will have single phase. So, the steam is passed through, the steam hits the turbine. So, the turbine has pressure, here it is pressure and temperature both are very high. So, when it comes out, it tries to do work and then the left with pressure is low, temperature can be low or it can be the same, generally it is low. Then we try to pass this into the steam, whatever is there, pass through a condenser. In the condenser, it gets converted, again a phase change happens, from steam to liquid it happens, and then we try to send it back to the pump. It is a closed loop system. You can have an open loop system, you can reject this out, or you can use it in a closed loop system. Today, we use it as closed loop system, and every time when the loop is running, we might lose the water in terms of vapor which gets out maybe 3%, 4%. So, it is not a big loss, but still it is a closed loop. Their primary objective is to convert thermal energy derived from the fuel combustion or other heat sources into mechanical work, which can then be transformed into electrical energy. This is what I said, turbine blade, the work whatever is done gets attached to a generator, generator to electricity. The idealized Rankine cycle, often used to model steam power system, serves as a benchmark for understanding more complex real world application. So, we saw the same system here, it is the same schematic diagram used here. The vapor power cycle are central to sustainable and large scale power production, and studying their thermodynamic behavior enables engineer to optimize the performance. At what speed should I run the pump? At what energy I should try to, or temperature I should try to run the boiler. Boiler in the schematic looks to be very simple, but in real time it's a very tough machine to handle. Then turbine blades. The turbine blade, the blade geometry is a very difficult task, and you will have not one, the shaft is attached to one blade, it will be series of blades. By analyzing energy and entropy change at various stages of the cycle. So, why? Because you have heat which comes out, then you have entropy change. These two are very important. By analyzing the energy and entropy change at various stages of the cycle, we gain insight in both the limitation imposed by the second law of thermodynamics. Friends, all through the course you should remember zeroth law, first law, second law, and the engineering trade-off necessary for practical implementation. The Carnot vapor cycle is an idealized thermodynamic cycle. Why do we always go for Carnot vapor? Carnot cycle is because here to a large extent we remove all the assumptions, or I would put in this way, we try to have lot of assumptions and then we try to simplify the system to get the output. So, the Carnot vapor cycle is an idealized thermodynamic cycle that represents the maximum possible efficiency any heat engine can achieve operating between the temperature limits, two temperature limits. So, unlike the Carnot gas cycle which uses ideal gas, the vapor cycle uses a phase change, vaporization and condensation. Vaporization, here it is vapor, here it is condense of a working fluid like steam. Though it is impractical due to difficulties in compressing wet vapor and handling two-phase flow in turbines and pumps, it is useful as a benchmark for real vapor cycles such as Rankine cycle. When we plot the TS diagram, that is what I said here, operating between two temperature limits. You have a TS diagram, you can see here the temperature. First, this is a normal curve, you know what is it. So, here it is steam, here it is liquid, and inside this is liquid plus vapor. Vapor is the steam, right. So, here is a critical point. So, this is the diagram where in which TS diagram which shows at what stage the working fluid is in which state, right. So, now this is the basic curve, and then in this curve you can see 1 to 2 where there is 1 to 2, 1 to 2, right, where the temperature is constant, 1 to 2 where the temperature is constant, and then 2 to 3 there is an entropy drop, 2 to 3 there is an entropy drop where turbine blade is rotated. From 3 to 4, there is a condensation happening. Again, in an ideal cycle, we assume that the temperature is uniform. Then 4 to 1, we try to increase the temperature. 4 to 1, we try to increase the temperature. So, you see here, so 1 to 4, 1 to 4, and then 2 to 3, 2 to 3, there is a same entropy. So, S1 equal to S4, S2 equal to S3. So, this is a typical idealistic TS diagram for Carnot vapor cycle. So, I would like to reiterate this point. Though it is impractical due to difficulties in compressing wet vapor and handling two-phase flow in turbine, two-phase flow is very tough to handle, because what are the two phase? You will have steam and then you will have a liquid. The liquid, if there exists in droplet form and it is coming up with very high pressure, when it hits the turbine blade, it might erode the turbine blade, and it will also try to do imbalancing. Moment there is an erosion, there is an imbalance. Moment there is an imbalance, the efficiency of the output is gone. So, we will always try to have a single phase. Handling two-phase flow in turbine and pumps, same with respect to pumps also. Compressor, when we do, from here if it has steam plus liquid, the pump also will try to have its difficulty. So, it is useful as a benchmark for real vapor cycle such as a Rankine cycle. So, we do not know the output of a Rankine cycle. So, we try to have a benchmark, then compare the Rankine cycle with it. So, 1 to 2 follows isothermal heat addition, which is evaporation process 1 to 2, 1 to 2. So, occurs at a constant high temperature T2, working fluid absorbs heat Q in and vaporizes at a saturated condition. So, friends, now onwards you please start noting out the saturated condition. What is saturated condition? So, 2 to 3 is isentropic expansion. The high pressure saturated or superheated vapor expands into a turbine. So, where it tries to hit at a turbine where pressures are high and temperatures are high. So, high pressure saturated or superheated vapor expands in the turbine, produces work while temperature drops from T2 to T3, T2 to T3. Then isothermal heat rejection, which is condensation. Here at constant low temperature T3, heat is rejected as the vapor condenses into saturated liquid. So, now what we do is, in reality, here also when the heat comes out, right, with the condenser, when we say the heat comes out, again here there will be lot of heat, residual heat. So, here we once again tap it from here and attach one more cycle, and we declare this one as a high cycle and this one as a low cycle. So, that the heat whatever gets rejected still it is used. So, 4 to 1 is isentropic compression. Liquid is compressed back to high pressure by using a pump. No heat exchange happens. The entropy at this point is constant. If you go back to the diagram, you can say the same representation. So, the saturated vapor leaves the boiler at stage 3 or state 3, enters the turbine and expands to state 4. The fluid then enters the condenser, where it is cooled to state 1 and then it is compressed to state 2 in the pump. The efficiency of the entire cycle is found out by TH minus TL by TH, which can be represented as 1 minus TL by TH. Practically, it is very difficult to add or reject heat to or from the working fluid at a constant temperature. Where is the constant temperature coming? TS diagram, T1, T2. This is S1 and S2, right. But it is comparatively easy to add or reject heat to and from the working fluid at constant pressure. Temperature is difficult, pressure is easy. Therefore, Carnot cycle is not used as an idealized cycle for steam power plant. However, ideal cycle for steam power plant is Rankine cycle, in which heat addition and rejection takes place at a constant pressure process. So, this point is very important. Why are we not using Carnot cycle as an idealized cycle in steam power plant? So, the limitation of Carnot vapor cycle is isentropic compression of wet vapor is impractical, because it has a very high specific volume, possibly it can damage the compressor. So, isentropic compression of wet vapor is impractical. Isothermal process requires large heat exchanger. Heat exchanger means where there is a transfer of heat happening between high to low temperature. Okay. So, when it is done from high to low temperature, there is a heat exchanger done, and majority of the heat exchanger works with 30 to 50%. I am talking about very generic, but majority of the time it operates between 15 to 30% efficiency. So, you see there is a huge heat loss or energy loss. Two-phase expansion in turbine is difficult to maintain and it is inefficient. Used for benchmarking, but not feasible for real world implementation is the limitation of Carnot vapor cycle. So, this pushes us to study about the Rankine cycle. Rankine cycle is the fundamental thermodynamic cycle that underpins the operation of steam based thermal power plant, which produces a significant portion of the world's electricity. It overcomes Carnot cycle's impracticability of compressing a wet vapor by instead compressing the working fluid in its liquid state. So, this is where is the change, impractical of compressing a wet vapor by instead compressing the working fluid in the liquid state. This cycle involves pump, heating, expansion and condensation. Pump, heating, right. So, each of which is thermodynamically more feasible and mechanically more efficient than corresponding to the Carnot cycle process. The Rankine cycle is widely used due to its flexibility and adaptability to various modifications which are aimed to improve the efficiency of the output, such as superheating, reheating, regenerative feed water heating. All these things are possible in a Rankine cycle. So, you can keep on adding some subsystems to the main system and try to extract heat so that you are more efficient. So, the cycle begins with pumping a saturated liquid water at a high pressure. So, pumping. So, you say here water comes here, pump happens here at a high pressure, pressure increases. High pressure followed by heating in a boiler where it gets converted into a dry, saturated or a superheated steam. So, what comes out here is steam with very high pressure and temperature. The high energy steam then expands through the turbine and produces mechanical work, which is typically converted to electricity using a generator. This is what I said. After expansion, which happens in the turbine, what is expansion? The pressure is low, pressure goes down. After expansion, the low pressure steam, whatever comes here out, here also you will have steam. It is not that you will not have steam, you will have steam. The low pressure steam is condensed at here back into a saturated liquid in a condenser, completing the cycle. So, if we draw a TS diagram, it follows 1 to 2, 2 to 2 dash, 2 dash to 3, 3 to 3 double dash, from 3 double dash it falls down to 4 double dash, from 4 double dash it gets connected to 1. So, you can see, or the system can be drawn like this 1, 2, 3 and 4. So, understanding Rankine cycle is essential for engineers and researchers engaged in the design, analysis and optimization of modern power generation system. So, you have a PV diagram. 1 is the stage where you have pumping, 1 to 2 pressure increases, the volume is compressed, volume goes down. From there you move to 3 where there is expansion of volume, but the pressure is constant. From 3 you come down to 4 where you reduce the pressure and further expand the volume. Then when you want to complete the cycle from 4, we try to compress at a same pressure. This is a normal cycle, right. The other way around is you can try to go from here to 2 dash where the volume is compressed and the pressure is increased. Pressure, let us assume P1, this is P2, the pressure is increased. Then from there you allow the volume to expand, and then what you have is after the volume gets expanded, there is a increase in the further volume increase to 4 dash. Then from 4 dash you go to 1. This is one path. The other way around is you move from 1 to 2 or to 2 dash. From there you move to 3 double dash. So, why do we move to 3 double dash? Because this is steam, this is liquid plus vapor, this is liquid. So, if I want to make it this, I will make it as vapor. So, you enter into the vapor regime from 2 to 3 dash, and from 3 dash you try to reduce the pressure which happens in a turbine and which comes and hits at the downside of the curve where there is a volume expansion also happening. From 4 double dash back to 1. So, PV diagram Rankine power cycle goes in this form. When we wanted to put the same thing in a TS diagram or a HS diagram, you will try to have this phenomena. 1 to 2, the water from the condenser at low pressure is pumped into the boiler at high pressure. In this process is reversible adiabatic. So, water at low pressure is pumped to boiler at high pressure and it is reversible adiabatic. Note down this point. The water is converted into steam at a constant pressure by the addition of heat in the boiler. 2 to 3, constant pressure. 3 to 4 is reversible adiabatic. So, here it is reversible adiabatic expansion of steam in the steam turbine. At 4 to 1, there is a constant pressure heat rejection in the condenser to convert condensated into water. The steam leaves the boiler may be dry or unsaturated, wet or superheated. The corresponding TS diagram can be 1, 2, 3, 4, 1, which we saw. It can be 1, 2, 3 dash 4 dash 1 or it can be 1, 2, 3 double dash 4 double dash 1. It can try to work on any of these cycles. So, the thermal efficiency overall can be figured out by W net divided by Q in, net work done by Q in. So, it is H3 minus H4 into H2 minus H1 divided by H3 minus H2. So, this is how you try to find out the thermal efficiency of the process, work net. So, all the losses happening everywhere and then you try to figure out what is the output it comes divided by Q in. So, H1 is the enthalpy at the condenser output, H2 is the enthalpy after the pumping, H3 is enthalpy after boiling and H4 is after the expansion of turbine expansion. So, the reason for considering Rankine cycle as an ideal cycle for steam power plant is it is very difficult to build a pump that will handle a mixture of liquid and vapor at state 1 and deliver saturated liquid at state 2. But that is why we try to take the Rankine cycle. It is much easier to completely condense the vapor and handle only liquid in the pump. That is easy. You bring it to one state, water can be pumped. In Rankine cycle, the vapor may be superheated at constant pressure, that is from 3 to 3 double dash without any difficulty. So, what am I trying to say? It can move from 3 to 3 double dash easily without any problem. In Carnot cycle, using superheated steam, the superheating will have to be done at constant temperature along path 3 to 5. During this process, the pressure has to drop. So, when we are trying to increase the temperature, the superheating will have to be done at a constant temperature along path 3 to 5. So, during this process, the pressure has to drop. This means that the heat is transferred to the vapor as it undergoes expansion during working. This is practically impossible or very difficult. That is why we are always trying to talk about Rankine cycle when vapor cycle is discussed. The basic Rankine cycle, while widely used, suffers some amount of limitation. Primarily, its moderate efficiency and the moisture content at the turbine exit are putting some amount of limitation. So, we are trying to convert this Rankine cycle into modified Rankine cycle. To address this shortcoming, we are getting into modified Rankine cycle. There are two most common modifications done. One is reheat Rankine cycle, the other one is regenerative Rankine cycle. Reheat Rankine cycle improves turbine work and reduces moisture content, whereas regenerative Rankine cycle increases thermal efficiency by preheating the feed water. So, what we are trying to say is, wherever there is a heat getting rejected, please do not reject it and leave it in the atmosphere. Take that heat, try to convert the liquid into steam and then try to use the process. So, improves the turbine work and reduces the moisture content is by reheating. So, when you reheat, the moisture content will be reduced. So, it gets into superheated. Regenerative is the thermal efficiency can improve. These modifications make power plant more efficient, reduce the fuel consumption and extend the life of it. So, the modified Rankine cycle, the cycle goes from 1 to 2, where constant pressure, then 2 to 3 there is an expansion in the volume and there is a reduction in the pressure, right. While going to 3, in between we try to have an intermediate point which is called as 5. From 5 we try to drop down to 6, the pressure is further dropped down and then we close the cycle to 4. So, this is the PV diagram 1, 2, 5, 6 and 4 is the PV diagram for modified Rankine cycle. The explanation we have given it early. If we want to put the corresponding TS diagram, it is going to be 1. So, we are going to go to a temperature T1, T2 and then maintain the S up to stage 2, where the entropy is increased, S is increased, right. And then from 3 we drop it down to, from 2 we drop it down to 3, the temperature is reduced from T2 to T3 and the entropy is constantly maintained. So, rather than going to 3, we stop at 5 corresponding here, then we join it with 6, 5, 6, 4. So, this dashed area we will see what is the use of it. So, the process 1 to 2 represents the admission of high pressure steam into the engine cylinder. The process 2 to 3 is the reversible adiabatic expansion of steam in the cylinder and process 3 to 4 is the exhaust of the steam into the condenser. So, the net work done in the area 1 to is nothing but 1, 2, 3 and 4, 1. This is the net work area done. Observe the area 3, 5, 6, 3, 5 and 6, this area. So, it is also 3, 5, 6 is very small and in order to obtain this small work, the cylinder volume must be increased from V6 to V3, V6 to V3, the volume has to be extended. Okay. This makes the cylinder very bulky. For this reason, the expansion process is terminated at point number 5. So, in order to have a smaller volume, machine small, we stop at 5. So, that indicator diagram becomes 1, 2, 5, 6, 4 instead of 1, 2, 3, 4, 1. 1, 2, 5, 6, 4. The work lost is small, but there is a large saving in cylinder volume. If you want to go from 6 to 3, the volume cylinder goes very high. So, we have to also optimize the volume of the machine. So, we stop at 5, drop it to 6. So, that the indicator diagram becomes 1, 2, 5, 6, 4. The work lost is small, but there is a large saving in the cylinder volume. If you reduce the cylinder volume, so then the efficiency of the engine goes high. The process 5 to 6 represents the release of steam into the condenser. 5 to 6, the process 5 to 6, there is a release of energy into the condenser, thus causing a cylinder pressure to drop from P5 to P6. From P5 to P6, cylinder volume increase P5 to P6, right. The process 6 to 4 is then exhaust of steam at constant pressure. So, 1, 2, 5, 6, 4 is called as the modified Rankine cycle. 1, 2, 3, 4 is the Rankine cycle. 1, 2, 5, 6, 4 is the modified Rankine cycle. So, the thermal efficiency of the Rankine cycle can be increased by increasing the average temperature of the heat addition and by decreasing the temperature in the heat addition. So, basically you have a liquid, you heat it. So, you try to increase the temperature, more steam. So, more steam, more work, and when it is also getting converted into water, you try to, so decrease in the average temperature of heat rejection. So, the thermal efficiency of the Rankine cycle can be done only by these two. So, the maximum temperature of a Rankine cycle is limited by practical consideration. So, temperature, how much maximum you can go. So, that depends on the material what you use in the machine. So, you cannot keep on be going to infinite. You have to stop at somewhere, so that the material does not get softened while doing the process. So, maximum temperature of the cycle is limited by the practical consideration. For steam as a working fluid, the following difficulty arises at maximum temperature. The critical temperature of steam is equal to 374 degrees Celsius and the critical pressure is 221 bar. It is not possible to work at that pressure. It is very difficult to work at that pressure, the temperature. Latent heat of vaporization decreases as the pressure increases. If high pressure steam is expanded, the high degree of moisture content will present at the end of the process. If high pressure steam is expanded, the high degree of moisture content will be present at the end of the process. So, ideal working fluid for Rankine cycle should fulfill the following requirements. All the things are very important. Reasonable saturation pressure at maximum temperature. Then steep saturated vapor line to minimize moisture problem. Saturation pressure higher than the atmospheric pressure at minimum temperature, and then low liquid specific heat, so that most of the heat is added at maximum temperature. Non-toxic and non-corrosive working fluids you have to consider. You can get by changing the pH of water, by adding something towards acidic, moving towards basic. You can do all those things, but it will try to bring in non-toxic and non-corrosive. It should not corrode the thing. So, reasonable saturation pressure at maximum temperature we saw for 221 bar for water, steep saturation vapor line to minimize the moisture problem, then saturation pressure higher than the atmospheric pressure, low liquids specific heat. So, please check what is low liquid specific heat. So, for maximum temperature, all the above requirements are not met by a single working fluid. So, in binary cycle we try to have two different working fluids, that is why it is called as binary cycle. In binary cycle we will have two working fluids and used in order to obtain good results. So, mercury and steam are most commonly used working fluids. So, next we will move to ideal jet propulsion cycle. So, this is propulsion cycle is always used in the aircrafts. So, the gas turbine engine are widely used to power aircrafts because of their light weight, compact and high power to weight ratio. See, the same vapor pressure you can't put it inside an aeroplane and take it and go. In aeroplane also you need to have very high speeds coming up. So, we always have aircraft gas turbine operate on an open cycle called jet propulsion cycle. Some of the major difference between gas turbine and the jet propulsion cycle are the gas are expanded in the turbine to a pressure where the turbine work is just equal to the compressor work, plus some auxiliary power for pumps and generators. The net work output is 0. The major difference between gas turbine and jet propulsion cycle are the gas expands in the turbine to a pressure where the turbine work is just equal to the compressor work plus some auxiliary power of pump and other generator. Since the gas leaves at a very high velocity, the change of momentum that the gas undergoes provides a thrust to the aircraft. Now, you should understand, friends, how do you get the thrust while moving in a plane, and the gas has to leave at very high velocities, then only you get that thrust, then only you can go at that high speed. So, in ideal jet propulsion cycle, the fluid passes through a diffuser. So, you can see here first is a diffuser, then you will have a compressor. So, diffuser, compressor means compress air, then you have the compressed air is burned. So, this is what it is, and then you have a turbine which rotates, and then you will have a nozzle where through which it exits into the atmosphere. So, the fluid passes through a diffuser. What is a diffuser? Diffuser is a portion where it is trying to focus towards and push. So, it is diffuser. So, from the diffuser it goes into a compressor. So, the compressor compresses the air or mixture, whatever it is. Then it tries to get into the burner, turbine blade and a nozzle. So, the fluid passes through the diffuser first, where it is decelerated. The gas pressure increases, is decelerated. So, it is reducing. Typically operate at high pressure ratios of 10 to 25 ratio, it happens. So, the pressure increases. So, if I draw a TS diagram, you can see 1 to 2, 1, 2, 3, the pressure increases. Then onwards the pressure is constant, the heat is in. Then 4, 5, 6, there is a reduce in temperature and the entropy is constant. 6 to 1, there is a constant pressure, but during the same time the Q heat is rejected. So, 3 to 4 and 6 to 1 is constant pressure lines. So, a diffuser 1 to 2 decelerates the incoming flow relative to the engine. First it decelerates, reduces the flow. A pressure rise known as a ram effect occurs. A ram effect occurs. Velocity reduces, pressure increases. It can be explained through Bernoulli's equation, which is this: pressure plus half times rho v square plus rho g h is equal to a constant. So, the pressure rise known as a ram effect occurs where velocity reduces, pressure increases. Then compressor, burner and turbine, which is nothing but 2 to 5, 2 to 5, 2, 3, 4 and 5, where 2 to 3 is isentropic compression, 3 to 4 is a constant pressure heat addition, which we saw. 3 to 4 is a constant pressure heat addition, isentropic expansion through the turbine during which the work is developed. 4 to 5 during which the work is developed. The turbine power just enough to drive the compressor. Air and fuel are mixed and burnt in the combustion chamber at constant pressure. So, you can see here we have represented constant pressure line. Air velocity leaves the turbine is small and can be neglected. The air velocity leaves the turbine. Where is the turbine? Turbine is here, right. So, 5 to 6 is nozzle, 5 to 6 is nozzle. So, 5 to 6, the straight line is nozzle. So, isentropic expansion through the nozzle happens, the air accelerates and the pressure decreases. So, you can see velocity and acceleration, these two terms are used. The gas leaves the turbine significantly higher in pressure than the atmospheric pressure. So, that is how it could gush it inside. Sometimes when you see fighter planes which go on your sky, you can see it would have left a straight white line behind it. So, that is because significant higher in pressure than the atmospheric pressure the gas leaves. The gas are expanded to produce high velocity, which is VE is greater than V initial, resulting in a thrust. The pressure at the inlet and the exit of the turbojet engine are identical. So, thus the net thrust developed by the engine is found out by this equation. Force is equal to m dot V exit minus m dot V inlet, which can be done as m dot can be taken common and then it is V exit minus V initial. After the burning is done, what comes out? So, after burn is popular in military aircrafts and it is used wherever a need for extra thrust arises, such as for a short takeoff or compact conditions. Afterburner is similar to a reheat device. It is located after the turbine before the nozzle. After the turbine before the nozzle, somewhere here. It produces a higher temperature and pressure at the nozzle inlet, resulting in an increased velocity and thrust. So, this is what it is. So, you have diffuser, compressor, then you have a burner which happens here and then you have a turbine which is there. There you put a afterburner is put in 656 and then you have it. So, now the same after heat burner you do. So, you will see there is a heat which is also added to the system. So, you get more thrust. So, 1 to 2 to 3 it is 1 to 2 to 3 is compressed. So, the pressure increases, then from 3 to 5 to the turbine there is a heat in which happens and then at the reheat portion. So, you will have 4 to 5, then again there is a heat in which is happening here. Then from 6, so 6 is nothing but burner to the nozzle exit, you have a temperature fall down and then from 7 to 1 is nothing but a constant pressure line where heat is rejected. So, 6 to 7 is a temperature drop. So, turbo pro is a term which is generally used. Gas turbine drives the compressor and the propeller, turbo pro, which is also part of an ideal jet propulsion cycle. Why am I covering all these things? Because today flight is something which fascinates you. I have been talking about steam turbine. So, now what happens in a plane? If you know that, then you will enjoy next time when you travel. So, a gas turbine drives the compressor and the propeller. Most of the thrust is from the propeller. Works as an accelerating large volume of air to moderate velocity. The propeller are best suited for low speeds less than 500 miles per hour flights. The bypass ratio is 100:1 or more. The bypass ratio is mass flow bypassing the combustion chamber divided by mass flow through the combustion chamber. So, these things are called as turbo pro. This is just a offset I have just said. A compressor is compressing, propeller which propels, which allows you to go. So, turbo pro engines are very small flights, they used to have turbo pro engines. So, in this lecture we first saw what is vapor power cycle, then we saw what is Carnot vapor power cycle, why is it considered, then we went into Rankine cycle, then modified Rankine cycle, then what are the considerations we had for a Rankine cycle as an ideal cycle for steam power plants, binary vapor power cycles, what are jet propulsion cycles, and finally, we saw what is vapor compression refrigeration system. These are the references which we have used in preparing the slides. Thank you.